Okay, hello and welcome back everybody. This is our worked example section for bases and vector representations. And to start out, I didn't actually include the definition of a dimension yet so far in this course, even though I suppose we've kind of implicitly been noticing what they are. But let's include that dimension here. Given a vector space V with associated basis, collection of vectors k equals 1 to n, the dimension of V is the number of elements in the basis. So in this case, I suppose when the basis clearly has, you start at 1 and you end at n, in this case, the dimension is n. But we can see here in some other situations, we could be like, okay, suppose that I define V to be the span of the vectors 1, 1, 2, 2, 1, 2, and 0, 1, 1. Now you must show this is linearly independent, otherwise it's not a basis. But supposing we do, suppose that it were linear independent, which it is, I'm just not going to go through the work of showing that, but supposing we do, the dimension is 1, 2, 3, because there are 3 elements in the basis set. Another great example of this would be these quadratic polynomials I've been referring to the entire semester, where we have a span of x squared, x and 1, has dimension 3. And we could come up with another crazy one if we wanted to. Maybe we'll call it F7, which is the span of the set e to the I n x, where n goes from -7 to 7. The question is, how many total elements are there? Well, if you start at -7, you end at 7, you'd think that it's 14, but you technically would skip over the number 0 then. So it's actually 15 because you include the number 0. There are 15. So dimension, and we often use this notation, DIMV equals 15. So that's really just all the dimension is. You just have to establish a basis and then count the number of entries in the basis. But what's something to add here, and that I've kind of hinted at the entire semester, is that there exist infinite dimensional vector spaces. It's an AL. Okay, so let's just look at one example. Suppose I'm considering the span of x to the nth power. N starts at 0 and it ends at infinity. So the span of this space, I should caveat for the mathematicians who are watching this, understood correctly with respect to normal convergence. But most of you watching it won't know what that means, and we're not going to worry too much about what that means. But if we think about the span of these elements, and technically it would be the closure of the span for people who understand what that means as well. But how many elements are in here? You start at 0 and you end at infinity. There are infinitely many elements here. In the basis. So the dimension of V is infinite. And in fact, most function spaces will be infinite dimensional. So let's just see maybe one example in this space. So one example, let's recall from the way that we can represent an element in the span, there's Einstein summation. So let's consider C, the sequence C superscript n, that's just directly equal to 1 for all n's. And then Cn x n, and actually I had my Einstein summation backwards because I want a subscript. Cn xn by Einstein. Einstein summation here will be the sum as n goes from 0 to infinity of C sub n x to the n but I just decided all the c's were equal to 1. This is x to the nth power. Recall from the series, or from the summation examples, this is actually equal to a function, 1 divided by 1 minus x, when x is less than 1. And so there is a very well-defined notion of taking linear combinations of infinitely many entries and recovering a function out of it. And so this is an example of a function in an infinite dimensional vector space. And so it's just good to keep in mind that we will periodically be working with infinite dimensional vector spaces, and the dimension is just referring to the number of elements in the basis. Let's move ahead to our actual worked examples for today. In our first example, let's do construct the vector in the space V equals the span. We're going to get used to some quantum mechanical notation here. Psi1, psi2, with vector representation -3, 4 plus I. And then I'm going to write the subscript, psi1, psi2. So those are our quantum mechanical states that we're going to serve as our basis for us. And we're going to construct a vector from the vector representation. So we're kind of going in the opposite direction of the previous video. Or the opposite direction of what's going on from the previous video is we know that we basically associate this as the coefficient of the first basis entry. And the second one is the coefficient of the second basis entry. And when we reconstruct those, we just have -3 times the first basis element plus 4 plus I times the second basis element. And so that's the reconstruction of the vector with that specific vector representation. And so it's just good to keep in mind that you can go in both directions when we encounter these vector representations. Let's just do one more example really quick. Construct the vector in the space V, which will just be C2 here, which will just be the span of 1 plus I, 1 minus I. The span of those two vectors with vector representation (2 minus I, negative I). That's going to be with respect to our basis above, which was 1 plus I, and 1 minus I. And so just as before, we're just going to look at this and consider it as the coefficient of this vector, and look here and say it's the coefficient of the other vector. So if we're going to write that out, then we just say 2 minus I is the coefficient of the vector 1 plus I, and negative I is the coefficient of the vector 1 minus I. And now you can see why it was very useful for us to get used to the complex algebra, because I'm going to be distributing these coefficients to each entry, and I'll have to FOIL in that first case. So when I FOIL the first case, I'm going to do my first outside, inside, last. My first gives me 2, my outside gives me plus 2I, my inside gives me minus I, and my last gives me minus I squared. And then distributing 2 minus I to the second term on the bottom, I just apply both terms to the I there, and I get 2I minus I squared. And the second vector, I'm going to distribute minus I all the way across, so I get minus I plus I squared in the top entry, and a minus I squared in the second entry. If I simplify all terms of the form I squared, right, every I squared is -1, so I simplify all those terms, and I end up with, so 2, this will be minus -1, so there's really a plus 1 happening here. So I get rid of that, and I do a plus 1. I get rid of this, and I get -1. I get rid of this, and I get, including that, and I get plus 1. And I get rid of that, and I get plus 1. So I'm going to have 2 plus 1, which is 3, plus 2I minus I is going to be plus I. I'll have 2I plus 1, or I'll write it as 1 plus 2I to put it in standard form. I'm adding that to the vector -1 minus I and positive 1. Vectors also allow me to add horizontally and add horizontally. This gives me 3 plus I minus 1 minus I. I end up with 2, and I end up with 1 plus 2I plus 1, also known as 2 plus 2I. And so this is now the vector that I started with, and let's keep in mind that this really is with respect to the canonical basis, right? We kind of covered in the last case where there's a lot of times where I'm dropping the subscript of vectors, and that's always assumed to be within the canonical basis then. So the canonical basis, which happens to be 1, 0, 0, 1. So if you drop the subscript, assume that it's in the canonical basis. Otherwise, we will include the subscript for you. Anyway, so that's how you would reconstruct the vector. So you can just see that you would reconstruct it with a specific basis, and now you know what your two entries in C2 are. This is an element of C2. Let's do another nice example, maybe in another function space. This is going to be pretty cool. So what are we going to have here? I'm going to say find the vector representation of cosine 2 theta, which is an element of the vector space, which is the span of cosine squared theta and sine squared theta. Now, this is really interesting because it doesn't look like, upon immediate perspective, we want cosine of 2 theta to be a coefficient of our first basis element, cosine squared theta, and a coefficient of our second basis element, sine squared theta. But it looks like we won't be able to make that happen because there's a 2 theta there and there's a theta there and there. And keep in mind, this is very important, this cannot move out front. When we write cosine of 2 theta, it's not allowed to pass out front. So it's really stuck where it is on the inside of cosine. I'll make that clearer maybe by putting parentheses where they should be on all of these. Let's make it clear that these are all stuck where they are. But what we do have at our disposal is the double angle identity. The double angle identity for cosine is that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And at that point, we can actually see that A should be 1 and B should be -1. Hence, cosine 2 theta has a vector representation of 1, -1 with respect to the basis cosine squared theta sine squared theta. So that's kind of a very nice example. And actually we could ask something about, like, what is the dimension of this space, which is the span of the two of them. And hopefully everybody can immediately tell. You just count the number of entries in there that are linearly independent, mind you, but they are linearly independent here. You can mostly assume that you're going to be presented with linearly independent elements. So we have 2 elements, which gives you the dimension is 2. Okay, so just because it's a function space doesn't mean that it has infinitely many dimensions, because we decided to construct it with two entries here. Okay, and I do want to provide us with one example of an infinite dimensional space. And we're going to see how to construct this later, but for now, assume that e to the x is equal to the infinite sum, starting at 0 and ending at infinity, of x to the n over n factorial, where n factorial is defined by n times n minus 1 times n minus 2 times ... times 2 times 1. Some examples of that would be that 3 factorial is equal to 3 times 2 times 1, which is equal to 6. 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120. You can calculate this out for any positive integer. So just keep those in mind about the factorial when I write it down. By the way, 0 factorial is equal to 1. Don't ask me why. We can get into why, but for now, just be okay with 0 factorial being equal to 1. And so we have this notion for the exponential function that you may or may not have seen in the past. We're going to assume that that's true. Let's find the vector representation as a quote-unquote vector of C infinity of e to the x with respect to the basis x to the n goes from 0 to infinity. So because the exponential has a representation where you're taking a sum of these basis elements, then you can actually represent it as a vector where you're extracting the coefficients. In other words, we write e to the x is equal to some column, giant column here, and we'll just put some dots at the end of the column because it continues forever. But it's with respect to this basis, x to the n, when n starts at 0 and ends at infinity. So what needs to go into the column is this is the coefficient when n equals 0. This is the coefficient when n equals 1. The coefficient when n equals 2, and so on. And so it shouldn't be too bad. Let's just actually write out this summation explicitly. We can write it as x to the 0 divided by 0 factorial. That's because I'm starting here, right, at n equals 0. And then I move forward. When n is 1, it's x to the 1 divided by 1 factorial. X squared divided by 2 factorial. X cubed over 3 factorial. And so on. And I can make those factorials explicit, especially now that I know that 0 factorial is 1. So that's x to the 0 divided by 1. So I'll just have x to the 0 plus x to the 1 divided by 1 as well, because 1 factorial is also 1. X to the 1. X squared over 2 factorial will be 1/2 x squared. X3 over 3 factorial, 3 factorial is 6. And so on. And so now we can look at these coefficients. There's a coefficient of 1 here, a coefficient of 1 here, a coefficient of 1/2, a coefficient of 1/6. So that's what we're going to do in our representation and write out the coefficients as 1, 1, 1/2, 1/6, and so on. And so here we can actually construct a vector representation, even though we have to put some dots at the end of it. It continues forever, but we have a vector representation of a function with respect to a very specific basis of functions. So we're going to stop there today. It's a bit of a shorter video, but I hope that was insightful. See you in the next one. Bye.